Okay. Oops, I need to do one more thing. Sorry. Okay. Can you all hear me and see me? Okay. Anybody there?
Yeah, we can see you and hear
Okay.
you.
All right. Good. So we'll talk about the next lab, and I realized about my plan to do chapter 27 is probably too ambitious. I was trying to do it during the lab, and so I was trying to do chapter 27 early. I think what I'm going to have to do, and I didn't tell the other group yet, I'm going to probably postpone the chapter 27 web assigned homework a little bit, so that you can just focus on the lab. I think we're actually at a good pace in the lectures, so I can postpone the homework a little bit, because I didn't get through all the material I wanted to get through at the 9:30 class. So what I want to do is give you enough information so you can do the lab, okay? And you actually have information to probably do about half the homework, but that's okay. I'm going to postpone the homework for a while. So I'm assuming everyone's going to be okay with that. Okay. Yeah, I apologize for the mix-up. I was trying to do something different and it didn't work out. Okay. I had the homework for chapter 27 due. I changed it to the 24th, but I think I'm going to hold off even on that. Okay. There was a question about any homework due today. The only homework due today is the worksheet. Okay, the electric field worksheet. All right, so let's talk about the next labs. So the next lab is the multimeter. It's called a multimeter quiz, but it's a skill demonstration. Okay, it's lab 2. It's due on October 3rd. And then your properties of charge is due next week. And so next Wednesday, I'm going to take some time out of class and answer any questions you may have on the properties of charge lab. And I can tell that not a lot of people have started on it, because people are asking, do you have partners? And I did. People asking, you have partners for the properties of charge lab? And I did say yes when I talked about the lab. And so yeah, Sunny, the priority is chapter 23 homework right now. Okay, and I apologize for the confusion, sorry. Yes, so do the worksheet today, and then chapter 23 by Sunday. Okay. So this is labeled Lab 02. Basically, what you're going to do in the lab, you're going to have 7 things to do involving this device that's in your lab kit. It's a circuit. It has 2 bulbs and 2 batteries. And you're going to wire it different ways, and you're going to make measurements. You're going to make a video showing me that you can make those measurements and build the circuits. Okay, the video might be 10 minutes. Show me actually yourself wiring it. Okay, that would be nice to show me that how you're wiring it. I had one student who was really good at making videos. He actually did the wiring part in fast motion. So his video was like 3 minutes. Okay. When we do this on campus, one of us would test you on the spot. You come in, you say you're ready, and then I'd say, okay, go through the steps in the lab. And so basically, all you're going to be doing is going through the step in the lab. You can call it a multimeter quiz. You can call it a skills demo, whatever. Okay, or you can call it a lab. Basically, it's a lab that you need to show me that you know how to use this device, the multimeter, and you know how to build a circuit. These are in your kit, okay? You're going to be using this a lot. This is not the most important instrument for electrical engineer, the oscilloscope is, but you have to know how to use this, okay? It's very important. There's no lab partners for this, okay? Because you have to do it. You have to be able to do it yourself. But before I talk about the lab, I want to say a couple of things about some basic concepts involving circuits. Okay, I want to talk a little bit about the flow of charge in the circuit. I want to talk about the basic components of a circuit. So give me a few minutes to talk about that, and then we'll get into talking about how are you going to use the multimeter and how are you going to use this. Well, it's very hard for me to do this in front of the class, the way everything's set up right now. It's easier when you're here for me to show you that, because usually what I do is I actually bring out a bunch of multimeters and I have you play with them ahead of time so you can follow what I'm saying. It's kind of hard to do it online. Okay, so I want to talk about how we get electrons to move through a wire. In order for one to get a light bulb to turn on, like so, what does it take? What does it take to get that light bulb to go on? Okay? Well, oops, we need to get electrons to go through a wire. So the question is, how do we get electrons to move through a wire? Well, we need an electric field. So we need an electric field inside the wire to get electrons to move. Now let's say it's a uniform field. So then the work done, well, first of all, you're going to have a force on these particles. And in a wire, it is the electrons that move. Okay, in a wire, it is the electrons that move. So you put them in, you put a field inside here, inside a conductor. It's going to make the electrons move. The field's going to do work on it. And it's going to be equal to minus the change in potential energy of the electrons. What's causing the work? Well, we need a device that produces the electric field, and it turns out it's a battery. A battery is a device that will produce the electric field in the wire. It's going to do work in the same way that I do work when I take this marker and lift it up off the ground. And then when I let this guy go, the marker go, then the potential energy gets converted into kinetic energy. So the battery is going to convert electrical potential energy into kinetic energy of the electrons. The electrons go through the wire. As they go through the wire, they collide with atoms within the wire. And as they collide, they're going to give up some of their energy. That kinetic energy gets converted into heat. Eventually, all that energy is lost to heat. And you can tell because if you take the battery out of a circuit, the light goes off. Okay. So we need a battery to do work on the electrons in the wire. So how do we describe the battery? We describe the battery in terms of the amount of work per unit charge it does on the electron. Okay. So I'm going to divide by, oops, this should be a minus sign. I screwed up. We describe the battery in terms of the amount of work per unit charge it does. And we call this the change in electrical potential. We call V the electrical potential. We call delta V a lot of times the PD, the potential difference. It's also known as the voltage. Okay, so we describe the battery in terms of how much work per unit charge they do, which is a voltage or potential difference. I'm going to try to use the term potential difference because that's a more accurate description of the battery, although I fall into the trap of calling it voltage a lot. So you'll see in the multimeter quiz, it'll say PD a lot. PD means the electrical potential difference. It also means the voltage. And voltage is a bad term to use. You should really say voltage difference. Okay. The unit for this is the volts. So what a battery is a device that maintains a potential difference between its terminal. So it maintains the electrical potential difference between its terminals. Okay, that's what it is. And so when you hook up a light bulb turns on. Okay, it's because of the fact that there's always a potential difference between the two wires. And we'll find in chapter 25 that if you have an electrical potential difference in space, you have an electric field. Okay? We can think of the voltage analogously to like water pressure. We can use the water flowing through a pipe as an analogy to what we are discussing here. In fact, I put a video in the modules that illustrates that. By the way, I also put a simulator that's going to allow you to build this circuit before you do anything. Okay? You can play around with the simulator, and I'll show it to you later. It's really easy to build a circuit with a simulator. Okay? And if it doesn't work, with the simulator, if things don't work, you'll see like flames coming out in the simulation and stuff. Okay? You don't want things to go bad when you're actually doing the experiment. Okay? All right. So in order for us to describe our circuit, we need to know something about the battery. We need to know voltages. We need to know potential differences. Okay, we characterize our circuit, our elements in our electrical circuit, in terms of voltages and how much charge is flowing per unit time through that element. What I mean by element is like a light bulb or whatever. Okay. So the amount of charge flowing per unit time through some portion of the wire, some part of the wire, we call the electric current. Just like if you take a water hose and you shoot water out of the water hose and you try to figure out the flow rate. Okay. So let's talk about electric current. Now we've learned about voltage. Let's say something about electric current. Okay. Now, electric current comes in many different ways. We don't, it's not necessarily just in terms of electrons moving through a wire. If I have an accelerator that produces a beam of particles, we can talk about the amount of charge moving per unit time in space. Okay? We can describe it in terms of current. There's a device that collects the electrons and determines the amount of charge per unit time that's being collected on this device. And you get the current. If you've had electrochemistry, if you've had chemistry and you've done the electrochemistry experiment, you work with electrolytic solutions with positive and negative charges moving in the electrolytic solutions. Those are currents. Okay? One of the interesting things about current is this, that a charge moving to the left, a positive charge moving to the left, is no different than the effect of a negative charge moving to the right. Let me illustrate that real quick. By the way, I'm not always going to draw a battery like this. This is too cumbersome to draw a battery like this. So let me draw my circuit with my light bulb. And let's assume that when we describe what's going on in here, we have electrons that flow this way. So what happens when electrons flow this way? They're going to go from negative to positive, right? They can't go. You can't have electrons go this way because they would repel. Okay. So the electrons would flow here. So then this is going to become, if this loses electrons, this becomes more positive, right? If this loses electrons, this becomes more positive. This gains electrons, this becomes more negative. Correct? Okay. Now, what if, instead of saying electrons go through here, what if I say positive charge moves through my wire? Positive charge moves through my wire, then this is going to gain positive charge, and again, this becomes more positive. This is going to lose positive charge, this becomes more negative. So it doesn't matter whether I talk about electrons going this way or positive charge going the other way, the result is actually the same. There's no physical difference between the two. That's an important thing to remember. And that's an important thing to understand. Okay? And that's why I say a positive charge moving to the left is the same as a negative charge moving to the right. Vice versa. There's no difference. Because the effect is exactly the same. So let's talk a little bit about current. Okay, actually, one more thing before I talk about current. I want to talk about the flow of charge. And I shouldn't have erased my picture. When people studied circuits a long time ago, and I'm going to put a light bulb in my picture. For many years, people thought, oh, it's the positive charge that moves this way. And we call that conventional flow. Okay? It wasn't until around the Hall effect was discovered that we can do experiments on what's moving in the wire. It was discovered that it's really electrons that move through the wire. It's really negative charges that move through the wire. However, whether you analyze a circuit using the real electron flow or conventional flow, which was used for many years, you're not going to go wrong because of the fact of what I said earlier, that a negative charge moving to the left is the same as a positive charge moving to the right. Okay? You can use either one to describe your circuit, to analyze your circuit. Most people use conventional flow of current, even though from a physical point of view it's not correct, but from analyzing the circuit it's still okay. Makes no difference. Okay? So let's talk about current. And when we talk about current, we talk about the amount of charge passing through a surface. So let me draw my wire. Let me draw a cross-sectional area of the wire. And these are the electrons moving. That way. So you have a bunch of electrons drifting with some velocity. We'll call it drift velocity. Okay. You might think that's a big number, but we'll talk about it later. That's not a big number, the drift velocity. What I'm interested in is how many electrons go through this area per unit time. And it's perpendicularly through the area. And the reason why I say that is because I'm interested in the component of the velocity vector that passes perpendicularly through the surface. If I have a velocity vector that looks like this, the component that's tangent to the surface is not going to cause the electrons to go through that surface, right? It's only the component of V perpendicular to the surface is going to make the electrons go through. Okay. The current, we're going to define the electric current as the amount of charge per unit time that goes through here. And I'm going to call this I average, at least for the time being. If I want to make it instantaneous, then I gotta do this. I take the limit as delta t goes to 0. But let's just pretend let's work with averages for now. Okay. So that's how I'm going to define current. It's the number of charges per unit time that go through this area. So I want to look at averages because I can get a more physical description of what this means. So in a time delta t, how much charge goes through here? That's what I want to talk about. How much charge goes through this area in a time delta t? Well, first of all, how far do the electrons travel, or how many electrons go through this area in a time delta t? Okay. I can collect, in a time delta t, the electrons that were over here at t equals 0 can pass through here. So how far do they travel? Well, that's going to be L is V sub d times delta t. What volume of electrons pass through here in the time delta t? Well, it's going to be V sub d. It's going to be L times the cross-sectional area of the wire. This is the volume of particles that pass through. If I know the number of particles per unit volume, then the number of particles that pass through here is going to be N times V sub d times delta t times A. So that gives me the number of particles that go through there. But then how much charge passes through there? Well, let's assume each one of the particles that pass through this area has the same charge. Then if I multiply by the charge, oops, total charge is going to be delta Q is the value of each one of the charges times N B sub D delta T A. And since I define I average as delta Q over delta T, then I is going to be N V sub D times Q. Oops, hold on a second, let me rewrite that. Times A. And so this is the electric current. Okay, that's my electric current. That's the number of coulombs per second. Also known as the amp. Also known as the ampere. Maybe you've heard of the term amp. Okay, which is actually a big unit. A lot of times what we do is we talk about the current in milliamps. Or microamps. Okay, so those are, and this, the amp, an amp 2, 5, 10 amps, you see that in electrical appliances, for example. Microamps and milliamps you'll see in your computer. You'll also see amps in the computer when you look at the power supply to the computer, but then on the circuit board you're going to see milliamps and microamps, and maybe nanoamps. Okay. Yeah, Matthew, I didn't see that. Yeah, sometimes they call them holes, and I don't want to get into that. I'm trying to be as simplistic in my description, at least for here. Okay. Are we okay with this so far? How big is an amp? How big is a coulomb per second? How many electrons are going through here if I have an amp? Well, 1 coulomb per second. Let's divide it by 1.6 times 10 to the minus 19 coulombs per electron. What is that going to give me? It's going to give me electrons per second. This is how many electrons per second are passing through this area. Okay, that's a lot. So a little wire carrying one, a wire like this carrying 1 amp of current has this many electrons passing through its cross-sectional area. That's a lot. Okay, the amp is a big number. Okay. Now, like I said before, instantaneous current is just dq dt. I use average current just because we can picture where that comes from. And I'm going to say a little bit more about electric current later, not today, but in another lecture. Okay. So how are current and voltage related? In other words, if I were to make a measurement to measure current and voltage, how is the voltage and the current going through that bulb related? Well, an experiment was done many years ago for different materials. And what was done is the following. So I'm not going to draw this for the battery anymore. Okay, I'm going to draw something called a schematic diagram. And the battery, in a schematic diagram, at least one cell, is denoted with a big line and a little line like that. This is the positive terminal, this is the negative terminal. Two cells, I would draw two of those. The power supply, you can put like an arrow like this. Okay, and I'm not going to be super careful with my symbols. I guess if I was drawing a circuit for engineers, then I would be more careful. But I'm going to put something here, whether it's a light bulb or whatever. I'm going to call it a load. Okay. And an experiment was made to measure this voltage. Of course, in those days, they use a cell. Okay, they use a voltaic pile to do these measurements. All right, and then you have a load here. And they made this measurement and found out for certain types of load, you got a straight line for this graph. That I was proportional to the electrical potential difference across the load. Not all materials behave that way, but a lot of them do. Okay. The proportionality constant is defined as 1 over R. R is called the resistance. It's a measure of the opposition a material has to the flow of charge. Okay. It's a measure of the opposition to a flow of charge. That's what resistance is. The bigger the resistance, the smaller the current. And so, since we know the proportionality constant, we can get rid of this proportionality symbol, and we can write the following equation. It's usually written this way. And this is Ohm's law. Ohm's law is only true for materials in which the ratio of delta V over I is constant, independent of the applied voltage. In other words, so delta V a material obeys Ohm's law as long as this ratio stays constant. Okay. Now, if the material does not obey Ohm's law, you can still define the resistance this way. It just means that this ratio, the resistance doesn't stay constant. Light bulbs, for example, because the light bulb gets hot, its resistance changes. Although it doesn't obey Ohm's law, we can still define the resistance, but you have to define it at various values of V and I. Such materials like light bulbs are called non-ohmic, and you see one in the graph on the screen. Okay. There's a lot of materials that obey Ohm's law. Ohm's law is kind of like Hooke's law, right? With Hooke's law, if you take a spring and you stretch it too much, it ain't going to obey Hooke's law anymore. Same thing with Ohm's law. If you put too big a voltage on something, it ain't going to obey Ohm's law anymore. It'll get hot, it might burn. Okay. But we can still define resistance. The resistance is still delta V over I, just that if it doesn't obey Ohm's law, the R doesn't stay constant. And people forget that. Okay, people forget that this ratio has to be constant in order for a material to obey Ohm's law. You have to have a straight line when you make the graph in order for the material to obey Ohm's law. You can define R whether the material obeys Ohm's law or not. Okay? Questions on that? Now, what is the unit for R? Well, it's the ohm, named after George Ohm. Use the Greek letter omega. And ohms can be pretty big, and so our resistance can be pretty big, so we can describe things in terms of kilo ohm or mega ohm. Okay, let me write that better. And again, this is the symbol for the ohm. There's gig ohm too. Questions on that? So now we have three important concepts or quantities that are used to describe what's happening in a circuit. We have voltage, we have current, and we have resistance. Of course, there's other things too that we'll learn later on, but for now, those are the important things. So how does this relate to our lab? So let me show you the lab that we have to do. Let me switch windows real quick. This is what you're going to be working on. And so there's 7 things you're expected to do. You're going to film yourself doing the 7 activities that's listed there. Okay? And each one is worth a certain number of points. So you actually have a rubric within it. So the equipment that you need is this circuit. Oh yeah, by the way, I forgot to tell the other group. It comes with a screwdriver. So you got to use a screwdriver, okay, to make your electrical connections. So you're going to actually use this for example, to build that first circuit. Okay? You got to make it work. You got to show me that you built it, and show me that it works. It doesn't take long to build a circuit. Okay, the hard part is using the darn screwdrivers. When we're on campus, we have an easier way to build these circuits. Okay, we're trying to make the lab kit cheap. So the second one, you're gonna do a different arrangement of this, et cetera, et cetera. Okay, so part of it is you're gonna show me that you can wire a circuit, and part of it is do you know how to make electrical measurements? So your lab kit also comes with this device. It's called a multimeter. This thing can measure voltage, current, resistance, and measures other things. Okay. So what I'm going to do now is talk about how to measure voltage, current, and resistance. Now, let me do the easiest one to measure is resistance. So the first thing you want to do when you're measuring resistance is realize that the device that you're measuring the resistance of cannot be in the circuit. You cannot have the battery connected to the device. You do not measure the resistance of a battery. But you measure the resistance, for example, of the light bulbs. Okay, so I have two wires here. One here, and hopefully the wire doesn't fall off. And here's my meter. Let's see if I can point the camera down on the table. Here's my multimeter. Here's my board. I want to measure the resistance of this light bulb. So first of all, to measure resistance, you always have a common. So you're going to put this into a common. And then there's this thing that says volt, ohm, hertz. You're going to put the other wire there. Okay. And then on this dial, you want to find, this one's unusual because there's so many different values for the current, for the resistance. Usually they auto scale. There's only one value. But this one you can change the different scales. These represent the maximum value. So I set it to the 200 ohm scale. So let me put that down. And I'm going to take and it doesn't matter which way you hook it up because it's not in the circuit. So I connect it into the circuit and I measure the resistance. Okay, it says like 1.3 ohms. You guys, you can see that?
Yeah, we can see that fine.
Okay. If you want to, for fun, you can measure your body resistance. Oh, that scale is too small. Let me go up to a bigger scale. Well, that's pretty. There you go. You have to actually get a constant contact. It's hard to get constant contact with your fingers, but I'm measuring my body resistance. Okay. So everybody has a certain value for resistance. It's different for everybody else. So anyway. So the way I hooked it up directly to the device. It's actually called hooking it up in parallel. Okay. So measuring resistance is easy. You take it out of the circuit. And what its device is doing is running a current through the device or running a current through you. It's a small current, so you don't feel it. Okay? You don't feel that current going through your body. And based on the current it measures, because it knows the voltage, it can calculate the resistance. Okay? Now, what about measuring voltage? Let me just say something. I should have said from the beginning. When you measure something, let's say you measure temperature. You take a thermometer and you stick it in the water. When you get the temperature reading, the temperature of the water matches the temperature of the thermometer. So the value that you're measuring is also going to be the same as whatever the value the instrument has, right? So the temperature of the water is the same as the temperature of the thermometer. And that's when you know the reading of the temperature. When I measure voltage, the voltage across the battery has to be the same as the voltage across the voltmeter. Okay? When you're running current, when you're trying to measure current in your circuit, the current through your circuit has to be the same as the current through the ammeter. Otherwise, it doesn't make sense to make that measurement. Okay? When you're measuring the length of something, the length of the piece of paper is equal to the length of the measuring device, at least the tick marks. So having said that, let's talk about how to measure voltage. So let me go to the board. So let me draw a circuit with a light bulb. or actually, let me just modify that circuit. I'll just use a battery. I want to measure the voltage across this. If I take my multimeter, if I take my two leads, and just hook them up like this, this will allow me to measure voltage. Of course, I got to set this to measure voltage too. This is going to be on the letter V. I'll show you that in a minute. But if I hook up my multimeter to measure voltage like this, I guarantee that the voltage across the bulb is the voltage across the meter. Why? Well, let's say this is a 3-volt battery. So let's pretend this is 0 volts and this is 3 volts. Let's say I grounded this side. This is at 3 volts. The wires, the effect of the wires we're going to pretend is negligible because they're thin, etc. The resistance is very low. This is at 3 volts. This points at 3 volts. The other side of the circuit, if this is 0 volts, this is 0 volts, this is 0 volts, and this is 0 volts. So the potential difference here is 3 volts. The potential difference here is 3 volts. So notice that, so the voltage across here and the voltage across this thing is the same because this points at 3 volts. Because remember, the wire doesn't have any effect. Now, one property that the meter has to have is that it has a very high resistance. So when I make this connection, I got to be careful because I have given the electrons 2 paths, right? So if the electrons go here, they can go this way and this way. But I designed my voltmeter such that it has a high resistance so that no electrons go this way. It's like having water flowing through a pipe and it reaches a T, but I put a valve here that's closed. So no water can go that way. So the same amount of water goes through here. The push, the pressure, the water pressure is still the same. You can think of voltage as like water pressure. And so this connection is called parallel because the voltages across the two devices are the same. And so measuring voltage is actually pretty easy. It's hard to screw that up. Well, let me rephrase that. It's hard to damage the meter when you're measuring voltage. Although I have seen people damage the meter measuring when they were measuring voltage. So let's try to measure the voltage across the battery. So here's the 2 terminals of the battery. Okay. And here's our meter. On this meter where you see the letter V with the horizontal line, that's for measuring voltage. So I'm going to put it on a 2-volt scale because these batteries are 1.5 volts. And so one of the terminals is going to be on V, the other one on common. And I'm going to connect. By the way, if you hook it up backwards, that's okay because you'll just see a minus sign pop up. Red to the red. Black to the black. And it should read a voltage. Do you all see that? I'm measuring the voltage across this battery.
Yeah, I see that.
Okay. Or I can measure the voltage across this battery, or I can connect them in series, however it is. But you hook up in parallel. If I wanted to measure the voltage across the bulb, of course the bulb was not hooked up, I would just do this. I should get 0 because there's no battery hooked up. But let me hook up a battery to it. And now read something, right? The light's on. It's just hard to see because I'm covering it. Okay. I really should screw that man, but I don't have time to do that. And so measuring voltage is easy. You might put it across. You might have to put it on the right scale. Here, you have a 2-volt scale, 20 ohm scale. I'm sorry, a 2-volt scale, 20-volt scale, 200-volt scale, and a 1,000-volt scale. So this can measure. We're not going to be measuring 1,000 volts, okay? I'm not going to have you do that at home. Questions on that? So measuring voltage is actually not hard. You just put things in parallel. And you guys are not going to have trouble with that. Oops. Let me fix the camera, sorry. What you're going to have trouble with is measuring current. That one's the hard one to measure. Okay. So let me redraw my circuit. Let's talk about measuring current.
Yeah, I think your camera froze.
I froze? Okay.
Yeah.
Okay. Thank you. Here's my light bulb. Now I want to measure the current through here. In order for me to do this properly, the amount of current going through this thing has to be equal to the amount of current going through the meter. If I do what I did before, like that, that's not going to work. Because if I make the resistance large, and I want to measure current, if I make the resistance large here, then no current's going to go through the meter. If I make the resistance small, then all the current will go through the meter and none will go through the light bulb. And the light bulb stays off. And then you would be measuring the current through the meter as a result of the meter, not the bulb. And there would be a huge current. So you can't do that. So what would be the other way to measure current? Well, you have to actually put it in series. You have to put it actually in the circuit. And the resistance of the ammeter is small, so it doesn't affect the current. And whatever goes through the bulb will go through the meter. Because there is no path, there's no change in path, there's no other place the current charge can go. Charge can only go this way. Okay, you only have one path. If I put it in parallel, then I have more than one path. And that's not going to work. So you actually have to put it in series in the circuit. You got to do this right, because if you don't do it right, you will blow fuses. The reason you want to do this experiment is so that you learn how not to blow fuses. It's going to happen anyway. Accidents happen. Okay. Anyway, hold on a second. I have someone trying to get through into this classroom. Just 1 second. There's a class going on in here. Okay. Let me get back. Sorry, I was interrupted with someone's trying to come into the room. So, how do we measure current? There's actually another issue. In order for you to actually accurately measure the current, if the current's small, you actually have to have a large enough resistance to be able to measure the current. If the current's large, you got to make this resistance small. And so there's a bunch of different settings for measuring current. So if you look at this, there's a let's see, a 20 milliamp scale, a 200 milliamp scale, and a 10 amp scale on here. Okay, and you have to set it to the right scale. If you put it to the wrong scale, you might blow the fuse. I froze again, didn't I?
Yeah, you did.
Okay.
Okay.
So if you put on the 20 milliamp scale and you have 200 milliamps, you'll blow the fuse. So you have to put it on the right scale. So you actually have to estimate the amount of current you have ahead of time. So you do it properly. If you don't do that, you risk blowing a fuse. And so that for this thing, you have to take this red thing off, remove the screw, and then take the fuse out. You do have an extra fuse that came in your kit. Okay. But if you blow an extra fuse, you have to come here and pick up another fuse. Tyler has them. Okay, Tyler should be here. He's here most of the week. Okay, so I do expect people are going to blow fuses. Okay. All right, so to measure the current, if it's below 200 milliamps, you want to have, this is going to be a little bit different. You're going to be using this for measuring current, and this will be your common. If you're going to go above 200 milliamps, then you put in a 10 amp scale. Okay? You got to estimate how much current you're going to have ahead of time because you might blow the fuse. And so that's important. Another thing when you're measuring current. Let's say you set up your circuit and you're going to measure the current. You're going to put this on the 200 milliamp scale. I froze? Okay, sorry, I froze again. Before you turn this on, take out one of the leads and then go to the right scale. And then put it back in. The reason why I'm having you do that is because if you have this in the whole time and you switch and you accidentally hit the wrong scale, what's going to happen to your fuse?
It'll just blow.
You blow it. So always be safe. Before you switch to that current setting, remove one of the leads, put it to the right scale, and then plug it back in. Okay, that's important too. Well, I mean, I make mistakes too measuring current. Sometimes, I get lackadaisical and I'll blow a fuse. But yeah, you just want to be careful with that. Because every time you got to blow a fuse, you got to open this thing up and replace it. Okay? So that's one of the reasons why I'm doing this. We're doing this exercise is so that you learn the proper way of measuring currents. And by the way, the currents that we're going to be using in this lab are not very high. They're not going to kill you. However, there is a document called the fatal current that I put in the modules. 75 milliamps going through your body will essentially kill you. It's not a lot of current. But your body has a very high resistance, so it would take a significant voltage to kill you. Although your resistance depends on which 2 points in your body the current's going through, right? If it's going through a short distance, then you get a lot of current going through there. You don't want to get a lot of current going through your heart. That'll kill you. About 75 milliamps will kill you. Just be careful. Okay. When you're dealing with electrical stuff. Our labs, everything's gonna be low current, low voltage. We're not. Otherwise, we wouldn't give you lab kits. Okay. We're doing things with, everything's under 10 volts. So it's pretty hard to get electrocuted under 10 volts. Questions, concerns? Let me show you the simulator. Hold on a second. Let me go to a simulator page. So this is a module page. I want to find the simulator. Okay, this is from, I think, University of Colorado. And this will allow you to build circuits with the batteries and light bulbs and make measurements so that you can practice before actually making a video. So for example, let me get a battery and let me get a light bulb and wires. Light goes on. Okay. Let me disconnect this one. Let me get rid of that one. I'm going to put another battery in series. When I put two of them in series, it's going to be a lot brighter. Let me do one more thing. I'm going to put in series the meter. Let's put a wire here, wire there, wire there. And did I connect it? That's strange. I'm too far away from the screen. Okay, so there's my circuit with two batteries in series, and I'm measuring current. So you see what you can do with this device, right? You can play around with it. Okay. Questions? All right, I want to show you a couple more things, and then I'm going to stop. Let me go back to the PowerPoint. All right, and I gotta change something on my computer. Oops, I don't know what happened there. Okay, it's back. That's good. So let's talk a little bit about some terminology involving circuits. In fact, let me blow this up for you guys. Sorry, I'm moving my chair here. Let me go back one. This is a typical circuit.
Froze again.
Froze again? Darn it. I don't know why that's happening today. So that's a typical circuit with the load is the resistor. That symbol, that squiggly line, is the symbol for resistance. The picture showing the direction of electron flow, and the battery is a 3-volt battery. That's called electromotive force. That's actually not what the load gets. That's what the rating is. But real power supplies have something called an internal resistance. And so that causes the current to be lower than what it should be. And of course, the voltage across the load to be less than what it should be. We simulate the internal resistance as if there's another resistance in the circuit in series with the load. That's that little r. And what happens is that the voltage that is across the load is smaller than 3 volts. We call it the terminal voltage. That's the voltage it's actually getting. And that's because they have the internal resistance. And again, we're going to assume that any circuit we draw, the wire's resistance is negligible. Unless you're told that the wires have resistance that's significant, okay? Unless you're told about something about the resistance of the wire, you should ignore the resistance. Okay. This next slide shows you 2 resistors that are hooked up in parallel, but it also shows you a couple of things. Each closed path in a circuit forms a loop, and each loop can be used to analyze the circuit. This circuit has 3 loops. You see one there. There's also one that includes the 2 resistors. And there's also a third that goes on the outside that includes little r, the battery, and the big R on the outside. And any one of those loops can be used to analyze a circuit. Points where the current can branch off, they're called nodes or junctions. Okay. Let me say something about these 3, and then I'm going to stop. I'm going to have to go to the board for this. And hopefully the system doesn't freeze anymore. Okay. So let me draw the circuit up on the board. I have 3 batteries. That go to a load. Let's make my load a light bulb. And I'm going to ground one side, meaning that this is 0 volts. I just want to identify what everything is here. These are all 1.5 volt batteries. So the EMF is 1.5 volts. If I define this to be 0, I'm forcing this to be 0. By the way, on a battery, the potential difference is defined, but what value V is on either end could be anything, okay? Depends on how I reference it. So the potential difference is 1.5 volts, but what value this is could be anything. It's like saying, what's the gravitational potential energy for an object that's on the table? Well, I got to define my 0. All right, it could be any number. It's arbitrary. So either the value of either side is arbitrary, but the difference is 1.5. So I reference this to 0. I connect this to ground. This is a 1.5 volt battery, so this is 1.5 volts. Again, this thing is, either one of these is arbitrary, but when I connect this to this, which is at 1.5 volts, this is at 1.5 volts. And the battery maintains a potential difference between its 2 terminals. This is 3 volts. So since I connected this to this battery, then this is also 3 volts. And this has to be 4.5 volts. Wires have no resistance, so this is 4.5 volts. 4.5 volts. And then 0 volts. And so the voltage across the light bulb is going to be 4.5 volts. These 3 batteries are in series. Whereas if you have batteries like this, those batteries are in parallel. You're going to get 3 volts. I'm sorry, you're going to get 1.5 volts because they're connected in parallel. But this will last longer if you connect it to your bulb. Okay, you'll just get this. You'll get the bulb to stay on longer because you have two things connected in parallel. Whereas if you connected the batteries in series, it's like putting 3 water pumps one behind the other. You're going to triple the kinetic energy of the water. So you triple the kinetic energy of electrons, you're going to be dumping 3 times the energy into the bulb. Okay. Questions on that? Okay. So I'm going to stop at this point. And 'cause that's kind of where I stopped with the other group. And now I'm going to push the homework on chapter 27 to a later time. So don't even worry about the chapter 27. I would read it though. Okay, so please read chapter 27, but we'll deal with the homework later. Are we okay? Questions, concerns? Okay. Next Friday, I will not be here. Professor Shakel is going to run the lab. And so basically, she's going to be answering questions on how you wire the circuits. Okay? So if you don't have questions, then the class will be short. If you have questions, then, she'll answer questions until you're done, until the time is up. Okay? Let me check the chat real quick because I'm too far away. All right. You guys have a good weekend and you're welcome.
You too. Thank you. See you later.
Okay.